Hello, this is Dr. James Camp at Lee College in Baytown, Texas, and this is my introduction to the nervous system. Today we're going to talk about the general functions of the nervous system and the sort of organization of the nervous system from a number of different perspectives. This is the first system we've gotten to where there's a diversity of organs. Okay, there's the brain and the spinal cord and the nerves and the eyes and the ears. Uh, Previously, we've dealt with a whole lot of bones or a whole lot of muscles, but they are all essentially the same organ. Here, we've got a whole bunch of different organs that we need to find some way to organize in our head to make sense out of how they all work and connect together. Okay, so first off, the functions of the nervous system. Um, the core function of all nervous tissue is to quickly carry information around the body. And that information is carried around the body in the form of electrical signals. Now, when we say electrical signals, we'll learn in a future lecture where we talk about nerve signal conduction. Uh, we'll learn that those electrical signals are not like plugging a wire into a power outlet or a speaker into uh, a headset into your computer or something, those sorts of electricity running along a wire. Here, we'll have potentials, cell membrane potentials moving along the, uh, the length of a nerve. Okay, if we then back out a little bit and say that the main function of the nervous system as a whole, the reason our body evolved a nervous system in the first place, is to monitor changes in the external environment. Okay, is it hot? Is it cold? Um, is there a predator coming at me? Is there a prey animal that I want to go after? Um, all of those changes need to be monitored. And then also monitoring the internal body conditions. Am I warm or cold? Is my blood oxygen getting too low or my blood pH getting too high? Um, those internal body conditions. Is my stomach full of food or not? And then finally, the main function that we just talked about, monitoring the external environment and the internal environment, and responding to those changes. That's the important point there, is we're not just monitoring changes, we're responding quickly to those changes. That main function requires three functional roles. The first is called sensory, and that's the role of gathering information and relaying it to the spinal cord in the sense of quickly reflexively responding to something, or to the brain, which can make more complicated decisions. Um, there are sensors throughout your body that monitor internal and external changes, and those changes are called stimuli in nervous system terminology. Any change to your internal or external environment is a stimulus um, if it stimulates a sensor. Okay. Uh, Integration is the second major role. This is going to process sensory inputs and decide how to respond. Now, that decision can be a fairly simple one. I'm touching a hot pot on the stove. I need to withdraw my finger before it burns. Or it can be a fairly complicated one. Uh, I see a creepy stalker in the parking lot. I need to decide to take a different route to my car or uh, call the Lee College security to walk me to my car or something like that. So some of those decisions are fairly complicated. Um, the integration centers of our brain also store memories of past events. And the reason we developed memory in the first place, again, sort of an evolutionary perspective on this, is that we want to store what an effective or an ineffective response was. My family has just adopted a couple of kittens. Cute. Uh, and the the effective or ineffective responses that they're observing as, you know, if I pounce on this toy, I get a stimulus back that's exciting to my brain, so I should remember that pouncing on that toy is a good thing to do. That's an effective response. Jumping from this chair to that table that's too far away, I end up crashing and it hurts my belly. That's an ineffective response to a stimulus. I should remember not to do that in the future or to change how I do the behavior in the future. So that's the basic level of memory that humans have developed a much more complex memory. You are hopefully able to remember the words I'm saying right now and displaying on the screen here, but maybe you're not. But if you're not able to remember them right away, you'll go back and take a quiz on this later. You will get to answer questions about it in other parts of this class, and that will build more memories. And every time that you successfully memorize a fact in this class, your brain remembers that as an effective response and tries to help you remember that in the future. We remember persons, places, and things that meant something to us. That's sort of a uniquely mammalian trait. I don't think lizards, my son has some pet lizards, and I don't think they honestly remember which people in the family feed them and which people don't. But my cats do. My dogs do. They remember which people feed them, which people pet them, which people take them for a walk. They remember which people give them a bath and try to avoid those people sometimes. So, memories can be both positive and negative. We respond to sensory inputs by sending motor commands. And motor makes you think of motion, like, a car motor or a motor on a fan or something like that. Not all motor commands cause motion, but that's what we call them because some of them do. Some of them move. They all cause some sort of effect on your body, and so the organs that they connect to are called effector organs. The most common effector organs are muscle tissues, and that's why we get the word motor for this. But there are also glands that are effector organs. If you smell food, you reflexively send a signal to your salivary glands to salivate. If you're getting too hot, you reflexively send a signal to your sweat glands to secrete salt water onto your skin that can evaporate away and cool you down. So those are also motor roles, even though they don't produce motion. Okay. Enough general theory. Let's talk about the concrete anatomy of the nervous system. We can break the anatomy of the nervous system down two ways. One classic way to do it is to discuss the peripheral nervous system separately from the central nervous system. Peripheral nerves are those pieces of our body that receive information. Here comes the information traveling into the spinal cord or the brain. Or they send information. Here comes a motor command traveling out to maybe a muscle that I want to move. Okay, that is peripheral nervous system. And that comprises the cranial and spinal nerves. Okay. And it comprises the sense organs. We wouldn't be able to have this information to receive and bring into the spinal cord or brain if we didn't have sense organs to collect those stimuli. The peripheral nervous system is contrasted with the central nervous system, which processes information. We've got this information, we're going to maybe make a reflex loop out of it, or maybe we're going to take it to a higher brain center, which is going to process it to some extent, and then send it back after some thinking about it. This includes, therefore, the brain, okay, obviously processes information and makes decisions, but also the spinal cord. A lot of our most basic reflexive responses to situations happen in the spinal cord without any involvement from the brain. So you may not think of your spinal cord as making decisions, but it does. It decides if a pot on the stove is hot enough for you to jerk your hand back from it reflexively. That's a decision that has to be made. It's only much after that instant reflex that your brain becomes aware that you touched something hot, because it takes a little while for that information to trickle up through the several layers of the brain. Okay, one important difference between the central nervous system and the peripheral nervous system is that the central nervous system is enclosed in bone. Okay, see how I've depicted this as a unit here. The central nervous system is either the brain or the spinal cord. It is a single unit, and it is encased in protective layers of meninges and bone. The peripheral nervous system is not encased in bone or protective layers. You have these nerves that are just out there. They can get pinched, they can get severed. All sorts of damage happens to your peripheral nervous system throughout your life, and it has a remarkable ability to take that damage and regenerate over time. Central nervous system tissue generally does not have an ability to regenerate over time. If you've ever known someone who got their spinal cord crushed or severed, they were probably paralyzed in some parts of their body semi-permanently. Okay, you can sometimes recover a small amount of function after a spinal cord paralysis, but it's a very difficult process to get any kind of repair to happen there. That's one of the reasons why the CNS is so well protected, is that we don't want to run the risk of losing any function there. Similarly, if you've ever known a person who had a stroke, a loss of function to the brain, it is possible for other areas of the brain to take over those functions that you lost, but it's a slow and intensive process, requires a lot of physical therapy to retrain the brain to take over from a lost function event. So again, the central nervous system needs, it's so well protected because it needs so much protection. Okay, another way of organizing the nervous system is by region. Okay, and we can split the nervous system into two major regions, cranial and spinal. The cranial nervous system is run by the brain. It is centered around the brain, organized around the brain. This is the part of your nervous system that I say it's all in your head, because it literally is all in your head. The brain has multiple areas, a couple of cute little nicknames that we give to some of them. Your monkey mind, you might say, your conscious brain that is constantly swinging thoughts around like a monkey playing in the trees, is your cerebrum. The cerebrum is sometimes known as the most human part of the brain, because it is what gives us our personality, it's what gives us our memories, it's what gives us all of those things that we associate with thought, with conscious thought. There's a similar word, cerebellum. This is not a conscious part of your brain. This is a part of your brain that acts like a little supercomputer on the back of your brain that makes important calculations, like how to stabilize your body movements, or how to synchronize time information with other signals that your brain may be getting. If you've ever tried to sense um, how far apart uh, noises are, your cerebellum is helping you synchronize that time information. So the most classic role of the cerebellum is motor coordination, helping you synchronize multiple muscle movements, but we're learning more and more about it all the time, that it also helps in image recognition and um, time and space coordination and all sorts of things uh, that require kind of a computer processor in our brain. Another major part of the brain, what one evolutionary biologist calls the furry little mammal part of our brain, is the limbic system. This is, some people class this as part of the cerebrum, and some people exempt it from the cerebrum and say it's a separate part of the brain. Um, but this is the part of the brain that deals with, instead of conscious thought, it deals with sort of the subconscious emotional state of your brain. So we call it the furry little mammal part of your brain because it's the part that would cause a mouse to see something scary and scurry into a corner of the room, or that would cause a puppy to get mad at somebody uh, and swipe its little paw at you, or whatever. Um, so all those emotions, fear, anger. Someone once said that the limbic system has a few states: mad, sad, glad, um, and afraid. Um, and which of those states you're in determines a lot of things about how you can use your cerebrum. So, for example, a lot of you probably get very anxious before taking a test in this class. And then you find that information that you were sure you knew when you did the review the previous day um, are just not coming to your mind. That's because the limbic system is blocking your conscious access to those memories because it senses that you're in a state of stress and wants to prioritize survival skills that you have stored in your brain. So the important lesson from that is that if you want to uh, do well on a test, you need to be sure to relax yourself before you take the test. Do a little yoga at your desk or something before you take the test. Put your limbic system into its glad mood instead of its scared mood. And then finally, at the base of our brain, there is something called the brain stem, which is sometimes called the reptile brain by evolutionary biologists, because this is the part of our brain that we share in common with the most other animals in the world. It goes as far back, at least, as little lizards scurrying around on rocks, and possibly even farther back than that. But any animal that breathes has to have the breathing centers that are part of the brainstem. Any animal that has a heart has to have the heartbeat regulating centers in the brainstem. So these are very important, critical to maintaining life parts of the brain. Okay, so that's the central part of the cranial nervous system. Spreading out from that throughout your head and occasionally through other parts of your body are the cranial nerves. There are 12 cranial nerves. They are numbered 1 through 12, but they're numbered in Roman numerals. So when we get to those in Unit 6, you will find that you have to remember the difference between IX and XI as far as Roman numerals is concerned. And then all of the special sense organs in your body are located in the head. So we group those in as part of the cranial nervous system. That's your eyes, your ears, your taste buds on your tongue, and your olfactory fibers in your nasal cavity. The spinal nervous system is organized around the spinal cord. The spinal cord does not have a complex series of parts like the brain. It is one unit. It's organized sort of in a back to front and side to side way rather than a top-down sort of way. So at each level of the spinal cord, you'll find mostly the same structure. And so we're going to talk about the spinal cord a little bit in terms of gross anatomy, but mostly we'll talk about it in terms of what we call sectional anatomy. If you take a slice of spinal cord, what do you see there? Because it's pretty much the same at every level. Branching out from the spinal cord are spinal nerves. There are, I forget exactly how many of them there are. See, there are 8 cervical nerves, 12 thoracic, 5 lumbar, 5 sacral, and 1 coccygeal nerve. So you can do the math there. But these spinal nerves are numbered with a letter number system based on which part of the spine they come out of. So the 3rd cervical nerve would be C3. But those spinal nerves do not last very long as individual nerves. Most of them join up into network structures called plexuses. Okay, and then emerging on the other side, on the distal side of those plexuses, are what I call the named nerves. Some people still call these spinal nerves, but to distinguish between the spinal nerves that have numbers and the ones that have names, I just call them the named nerves. So these have names like brachial nerve because it runs through the arm, or, no, there isn't a brachial nerve, sorry. Radial nerve because it runs down the radius bone, or axillary nerve because it runs through the armpit, or femoral nerve because it runs down the femur. Also part of the peripheral nervous system of the spinal region are general sense structures, and these are distributed throughout the body. So everywhere that you have skin, you have touch sensors. Everywhere that you have skin and everywhere that you have several other organs, you have temperature sensors. Everywhere that you have any organ, you have pain sensors. Sometimes we're happy about that and sometimes we're not. And then there are other general senses, such as your sense of blood chemistry, that you're less aware of, but they're still distributed throughout the body. Okay, so if we combine these structural and regional perspectives, we can get a sense of the body's, the nervous system's organization as a grid. On one axis, we have spinal versus cranial. Okay. And on the other axis, we have central versus peripheral. Okay. And so this forms kind of a grid of spinal features versus cranial features and central features versus peripheral features. We're going to be taking apart the spinal cord, the nervous system for it's too much. The nervous system just has too many organs and too many functions and too many things to discuss to put it all into one unit of information and have one test over the whole thing. So what Dr. Ross and I do is take the spinal versus cranial approach. And so Unit 5 will deal with the spinal cord, the spinal nerves and their plexuses and named nerves, and we'll also cover the general properties of nerve tissue and how nerve signals are conducted in that unit. Then we'll take the cranial nervous system for Unit 6. We'll deal with the brain, the cranial nerves, and all of the special sense organs, focusing mainly on the eyes and ears because those are the more complicated ones. And that will be Unit 6. Actually, I lied. We reorganized slightly since this slide was made. This is Unit 4, and that's Unit 5. Unit 6 is the integumentary system. So never mind me. Okay, finally, last slide here. we can deal with the functional organization of the peripheral nervous system. Okay, the central nervous system's functional organization is much more complex than you can explain on one slide, especially when you get to how things work in the brain. So we're going to deal with that later. But the peripheral nervous system, it's fairly easy to say it splits into a sensory role and a motor role. And then the sensory role, we can split out into special senses and general senses. Okay, special senses have their own private sense organ in one spot in the body that does all of the sensation for that. So for example, your eyes, you have two of them, but you only have two of them, and they're in one particular place in your body on either side of your nose, and they do all of the visual sensing that our body has. Not all organisms follow that approach, by the way. There are some organisms that have visual sensors all over their body so that they get a general pattern of light around them, a general pattern of light and darkness around them, and if a predator comes up behind them from the back, the shadow that predator casts causes them to scurry away from that. Those are fairly primitive organisms. All of the really evolved species like lizards and mammals and such have consolidated their visual sense into an eye. General senses are spread out as parts of body organs. So for example, the touch is part of the skin, so everywhere that you have skin, you have touch sensors. We're going to cover that at the same time that we cover special senses in Unit 5, but be aware that that's not something that's just located in your head. Obviously, you touch things with your fingers all the time, right? We can also split up sensory roles into somatic and visceral. Somatic senses are the ones we recognize consciously. Those are the 5 senses you were taught about in elementary school: touch, taste, hearing, sight, and touch, taste, smell, sight, and vision. Visceral senses are the gut feelings. Literally, visceral refers to your gut organs, your viscera. They're the gut feelings that you have that you don't recognize consciously. Okay, you may recognize consciously that your stomach feels hungry, but that's because it relays a sense of emptiness to a part of your brain, which then relays to a part of your conscious self that you need to eat. But most of our visceral senses, we don't sense that way. If I asked you right now how much carbon dioxide there was in your blood, you would not be able to tell me, because that sense reports to a part of your brain that just isn't conscious. That's one of your visceral senses. If I asked you to tell me what the temperature of the blood in your heart is right now, you wouldn't be able to tell me. There's a visceral sensor that senses the temperature of various organs in your body, but you just get a general sense of core temperature, whether you just generally feel hot or feel cold. You don't get individual senses from each of those organs. Okay, so those are the sensory roles: special versus general and somatic versus visceral. In the motor role, we can make a similar distinction between somatic and autonomic. Okay, somatic motor voluntarily moves body parts, mostly. I say mostly because there is one major exception, and that is your breathing muscles are controlled by somatic motor nerves. Those are involuntary, though you can voluntarily override them. You can choose to take a deep breath or to blow out long enough to blow up a balloon, or things like, hold your breath while you dive to the bottom of a pool. But generally, during most parts of most of our lives, we're not voluntarily saying, take a breath, breathe out, breathe in, breathe out, breathe in, breathe out. What would happen when we slept? We'd suddenly stop breathing? No. Our brain involuntarily moves those muscles. But mostly somatic motor nerves connect to muscles that voluntarily move body parts. Interesting side note, just love bringing in comparative anatomy sometimes. Whales and dolphins do not have involuntary breathing control because they spend so much of their time underwater. They don't allow their brain to just involuntarily cause them to breathe. So dolphins and whales have to swim to the top of the water and then consciously think, breathe out, breathe in, and then they can dive again. So again, not all animals do things exactly the way we do. Autonomic motor involuntarily regulates body systems. Okay, these are the things that we literally have no voluntary control over. You cannot, you can suppress autonomic reflexes. You can try to keep yourself from vomiting or from sneezing, but we often have very little success at that. It just, the autonomic motor system overrides our somatic control, and we vomit or sneeze or whatever involuntarily. This also controls things like your heart rate. I challenge you to right now raise your heart rate. Okay, you can't do it. I mean, you could by suddenly like jogging in place or something, but that's an involuntary response to you doing something voluntary like jogging in place. But if you want to sit still and just change your heart rate, you can't do it. Some people say, you know, the people in the kind of new age biofeedback world, that there are ways to think your way into a slower heart rate and a lower blood pressure and lower stress and all of that. But that's beyond the scope of this class. For our concern, autonomic motor is completely involuntary. And so that affects cardiac muscle, like I said, speeding up or slowing down your heart rate. It affects smooth muscle tissues. So you could not, for example, sit here and decide that it's time to move food from your stomach to your small intestine. Okay, that's a smooth muscle activity. It happens involuntarily when the stomach decides that it has done enough digesting and the small intestine decides that it has room for more food. Okay, there's a communication back and forth between the stomach and the small intestine that is an autonomic motor communication and causes that involuntary activity to happen. Lastly, glands. If your mouth is feeling dry, you cannot consciously decide to secrete more salivary juice into it. If your body is feeling sweaty and you find that inconvenient, you can't consciously decide to stop sweating. Okay? Most of the glands in your body are also involuntary and therefore regulated by the autonomic motor system. Okay, we can divide autonomic into two more categories, which we'll discuss at the end of Unit 5. Sympathetic and parasympathetic. Sympathetic is often nicknamed your fight or flight system, okay? Because sympathetic takes over when you're under extreme stress, usually a physically threatening, stressful situation, okay? You have to marshal all of your strength to run away from a threat or to fight back against that threat. And by fight, we don't necessarily mean get in a fist fight. Okay, your sympathetic nervous system becomes active when you see a car crash happen 300 feet in front of you on the freeway, and your fight response is to slam on the brake, turn the steering wheel, do things that that get you out of danger. Okay, you're fighting back against that danger in a way that's also sort of a flight response. You're maybe steering around the situation or something. The classic example of the sympathetic nervous system is if you're hiking in the woods and you see a bear or a venomous snake or something like that, and you want to get away. Okay, your brain goes on high alert to scan your immediate area for any other hazards so that you know where to run. Your heartbeat increases, your breathing rate increases, the blood to your running muscles increases so that you can get effectively get the most power out of your muscles, and you get the hell out of the way of that dangerous animal in the woods. Another more modern example is if you saw your child walk out in front of an oncoming car. Same complex of things. Your brain goes on high alert, your heart rate increases, your breathing rate increases, your running and grabbing muscles get more blood so that you can dash to where the toddler is, grab them, yank them away from the oncoming car. Parasympathetic is sometimes called the rest and digest system. Rest because it's the opposite of fight or flight. It calms all of your organs down, slows your heart rate, spreads out your blood flow a little more evenly and more towards your digestive organs. Okay, it's also sometimes called the homeostatic side of our nervous system, whereas sympathetic is concerned with responding to a critical situation. Parasympathetic is concerned with maintaining homeostasis. The autonomic nervous system also handles human sexual response, which is neither a fight or flight nor a rest and digest system, so it doesn't break down as neatly. But it's been said that the autonomic motor system handles sort of the 4 F's: fight, flight, food, and the F word for sex. Okay. Anyway, so that's one way to remember the main functions of the autonomic motor system. Okay, so once again, we have somatic and visceral by sensory, somatic and autonomic by motor. We also have special and general by type of sense organ, and we have sympathetic and parasympathetic by whether it's more of a stress response or more of a homeostatic response. Okay, we'll get into all of these things in more detail throughout units 4 and 5. So this is just an overview, but I hope you've gotten what you need to picture the whole nervous system as a complex but organized unit. Okay. Keep studying, and I'll see you in the next few lectures.